Our next speaker is Prof Stefan Hell. He'll be joining us virtually for his talk entitled Molecule Scale Resolution in Fluorescence Microscopy. The Q&A session will be moderated by Prof Liu Xiaogang. Prof Hell, please.
Hello, can you hear me well? I'm going to speak about fluorescence microscopy, the molecule scale resolution. So throughout the 20th century, the resolution of any light microscope and also fluorescent light microscope was fundamentally limited by diffraction to about 200 nanometers. And the best resolving microscope at that time was the confocal microscope, which could provide some higher, say, contrast, but not a better resolution. Now, the turn of the 20th century witnessed the development of a new type of microscopy, namely that of stat microscopy, which showed that it's possible to overcome the diffraction barrier and as a result, get a spatial resolution that is substantially better, up to a factor of 10. So stat microscopy showed that there is viable physics, so to speak, in this world that allows you to get beyond the diffraction barrier, which people believed that it wouldn't be possible for fundamental reasons. Now, this factor of 10, of course, made a substantial difference, as you can see here, because you can see details in a cell, for example, that you couldn't see before. And this has led to a share of the 2014 Chemistry Nobel Prize, and this is the official poster of the Nobel Foundation showing the development of stat microscopy, or the working principles of stat microscopy, and the working principles of palm storm microscopy, which was a method that was developed about 6 years later, but has a number of, say, specific traits that made it very valuable. It also provided a spatial resolution increase roughly by a factor of 10. And it also operated on the same, say, physical principle, which I will speak about in a few minutes, namely to separate molecules, fluorescence molecules, by turning them on and off. But the difference here in palm storm was that the molecules were turned on and off individually, stochastically in space, whereas in stat microscopy, the molecules were turned on and off using a, say, structured pattern of light, a beam of light that had a clear shape in space. Now, each of the methods has advantages and disadvantages, of course, but one thing that they have in common is the fact that they can, in principle, attain a spatial resolution that goes down to the size of a molecule, so to about 1 nanometer or so. But in reality, at the time the Nobel Prize was given, the resolution was not better than 20 nanometers or so. So it provided, both methods provided an increase by a factor of 10, which of course was substantial. Nonetheless, they did not attain the ultimate limit, which was the resolution at the size of the molecule itself. What does that mean? It means that if you have molecules that are just 3, 4, 5 nanometers apart, you couldn't tell them apart at the time the Nobel Prize was given, because that was still too close, you know? And the size of a molecule is about 1 to 2 nanometers, so you couldn't distinguish them. Therefore, I'd say that while the microscopes crossed the threshold, as it was put here on the poster, I'd say that they did not attain the ultimate limit. And this is the reason why in my lab, after 2014, we put a lot of emphasis to get down to the ultimate limit, to get a spatial resolution that reaches, say, the 1, 2, 3 nanometer scale, so the size of the molecule itself. Now, in order to get there, of course, you have to understand what makes, say, nanoscopy, fluorescence nanoscopy, or super resolution fluorescence microscopy, some people call it, what makes it tick. And in order to explain this to you, I'm preparing just a few slides. So don't worry if you didn't understand how the principles of these methods come about. I'm going to explain it now, and don't worry about it. It'll be very simple. Now, the problem, or the reason why people said that it's not possible to get a spatial resolution that is below 200 nanometers was the fact that you cannot focus the light more sharply than down to about 200 nanometers. So if this is the spot size of light, the smallest that you can create is this greenish circle, then molecules that are just, say, 11 nanometers apart, like those that are arranged here, on this pattern cannot be discerned. Why? Because that big blob of light would make all of them shine at the same time. So basically, they were illuminated with light, and then they would say scatter light back or fluoresce light back, and then since they would do it at the same time, because they illuminated at the same time, it wouldn't be possible to distinguish them. So the key solution to the problem, and this applies to any of these methods, STAT, Palm, Storm, and there are many acronyms by now, PAINT, whatever, or some people call it single molecule localization. The essence, really the real essence of it, is the fact that you make sure that despite the fact that all of the molecules are illuminated at the same time, not all of them are capable of emitting light back, so scattering light back, fluorescing light back. So even though there is this green beam of light, what was the key element here is that there is a mechanism, one sort of mechanism here, in one of these molecules, or in these molecules, that make sure that they do not emit. Only this one is emitting. And because this one is emitting, you can discern it from the rest. You may not know which one it is, yeah, but you know it's only one, and this one is distinguishable from the rest. And then how do you get the other ones? Well, you have to turn this one off, and then you get the next one, and the next one emitting, and then that one off, then you get the other one emitting, but the other ones here, the black ones, have to be off. And this on-off principle allows one to distinguish the molecules, so to notice that these are different molecules. It's not just one molecule. And this is actually, this single molecule on and off switching is a hallmark of the Palm-Storm principle. But if you turn molecules individually on and off, of course, you have the problem that you don't know which one it is. I mean, it could have been also this one, that one, that one. So how do you know it's this one? Well, the way you find out which one it is that you find out where the molecule is actually sitting, where it's actually placed, where it's actually located. And this is done by calculating actually, or finding out the position where it has been emitted. So the next step is not only to discern them, say by turning them on and off, but also to find out where they are with the highest possible precision. Okay, and so if we find out, yeah, where the molecule is, then we know it must be this one, because this is the position from where it's emitting. And this is done in Palm-Storm by a process which is called localization. I will talk about that in a minute. And then, of course, everything depends on how well you can localize individual molecules. Now, the problem with the way they were localized in this Palm-Storm method was the precision was not good enough, as I'm indicating here, because if the precision is so bad, as you can see here in the circle, that it's actually larger than the distance between the molecules, then you cannot tell them apart. You know, it doesn't work. If the precision is so bad, who knows that it's this molecule, could also have been that molecule or that molecule or that molecule for that matter. So in Palm-Storm, while molecules were discerned individually, which is very, very good, of course, the precision was insufficient to find out exactly which molecule it was, simply because the precision of localization was not good enough. And this is why I looked into this problem again to find out if there's a better way of localizing molecules. Now, before explaining to you why there's a better way and how it works, I'm just showing you now why the standard method doesn't work well. So in a typical, say, Palm-Storm experiment, single molecule localization experiment, we find the following setting. We have a microscopy arrangement where we have an objective lens, of course, and there is a light source, a laser, for example, and then there is a molecule here in the sample region. And usually the molecules are illuminated, or the whole field of view is illuminated uniformly, and then there is a molecule here, and now we need to find out where it is. So what it's done, usually the fluorescence is collected, the fluorescence emitted by the molecule. It is focused onto a camera, the one that you see here, many pixels, and then what will be produced on the camera, a blob of light. The blob of light will be nothing but the fluorescence diffraction pattern produced by a single molecule. So because fluorescent light is diffracted as well, we get here a blob of light here that is wide, that is relatively wide. Okay, and then the position is found out just by saying, and this is to some extent justified, that the maximum of this pattern must coincide in space by simple geometric optics with the position of the molecule. So you can say that if the molecule is here, then the pattern must be here, and if the molecule shifts a bit to the side, the pattern must also be shifted to the side. So, but the maximum must always coincide by geometric optics with the position of the molecule. And then everything boils down to calculating the maximum of emission here on the diffraction pattern. And that precision here, with which you can calculate that, scales inversely with the square root of the number of detected photons on the camera. So the more photons you detect, so the brighter the pattern is, of course, the better you find out its maximum. This is not surprising, because if you have just a few photons, then the pattern here will be noisy, then it's very difficult to find out its maximum. However, if there is many photons making up that pattern, then of course the pattern will be very well defined. So this is why the precision scales with the number of detected photons on the camera. So bright molecules, of course, give very high precision. Now, this principle of maximizing the number of fluorescence detection comes with problems. Why? In reality, if you work with fluorescent molecules, and that's what's done in fluorescence microscopy, of course, the number of emitted photons is limited by bleaching, because the molecules, like the fluorophore, they tend to fade out, like colors in your genes or whatever, they bleach. Of course, this is also the case for fluorescent molecules. There's another problem. If you need many detected photons, the method is slow because you need to wait. And then there is another problem, which is even more serious. Of course, fluorophores and molecules in general are, and also atoms, are dipole emitters. So meaning that they do not emit uniformly, they emit in certain directions. And therefore, if they turn their position in space, the pattern will be shifted as well. So it's not true that the maximum of emission just always coincides with the position of the molecule. And this can be off by a serious amount, 10 nanometers, 20 nanometers. And this also contributes to the fact that this method is limited in the actual precision that you get. Okay, now, what is the solution to the problem? And the solution to the problem is, in retrospect, of course, very simple. And the reason why I got this idea was that I worked on STED microscopy, and STED uses donut-shaped beams. And what I realized is that the hallmark of a method like STED is that you inject the coordinate in space with a beam of light. And this is actually what we're going to do now in order to find out the position of the molecule. So rather than using an uniform illumination of light, so in this new method, which I'm calling MINFLUX, we use a pattern of light that is shaped like a donut. And of course, this pattern of light perfectly defines a coordinate in space, which is the zero of that intensity, zero intensity value of the donut here in the center. And then, of course, this is perfectly determined by the incoming beam, because the laser has many photons, and you're not limited number of photons that would determine, of course, the position of the molecule. And then it's very easy. Everything boils down to finding out the position of the molecule, the unknown position of the molecule, with respect to the position of that donut-shaped beam, or to be precise, with respect to the zero of the donut-shaped beam. Now, if they are quite far apart like this, and here, this is light, of course, for exciting the molecules, then you can imagine the molecule emits very brightly, because there's a lot of green light that would excite it, and that fluorescence would be measured here by the detector. Okay, but if the two coincide in space, then the zero of the donut coincides with the molecule, of course, and then there is no excitation, because here the intensity of the donut is zero, and there will be no detected light here, because the molecule will not emit. So, in other words, the brightness will indicate how far the molecule is away from the zero. If it's slightly away, there will be some emission. If it's far away, like here, there will be strong emission. Just notice that there is no camera. So here we have a normal detector that just counts the number of emissions. So we don't need a pattern of light or something that we measure, just plain photons, brightness of the molecule. And I'm telling you now why this concept actually saves a number of detected photons. Why this concept is so powerful? So in order to explain this to you, I decided to introduce a demon. It's kind of like Maxwell's demon. And like all demons, the demon knows something that we humans wouldn't know. And I'm explaining to you the power of this conceptual, of this concept of introducing a demon. Now let's imagine for the moment we need to find out the position of the molecule, or the demon needs to find it out, but the demon knows where it is. So what does the demon do? The demon acts on the beam to shift it around, and always shifts the beam, the excitation beam, such that the zero coincides in space with the position of the molecule. Always coincide in space. Now, if that is the case, of course, there will be no emission here. There was no fluorescence emission at all. Yet, the demon could, of course, perfectly tell where the molecule is. Okay? The demon could perfectly localize the molecule in space, although the molecule is moving, would always know where it is. Why? Because the demon knows that it must coincide in space with the position, the molecule must coincide in space with the position of the donut. And so the power of this thought experiment is that it shows that you can come up with a concept for localizing the position of the molecule where there is no fluorescence emission. There's no detection. We do not require the molecule to emit. Now, remember, in the previous case, in the Palm Storm case, you require to maximize the number of detected photons. Here, what you do conceptually, at least, you minimize them. You put them down to zero. And this is, of course, very advantageous. Why? Because it makes the method fast. If you don't need to wait to get many photons, it's fast. It's more precise because the photons are very informative, of course. And of course, it's therefore much more powerful than previously. So what we do is we actually try to avoid fluorescence emission rather than to maximize it. And then there's another point. There is no wavelength dependence anymore in the scheme, which is striking if you're a physicist and say, oh, come on, this is all diffracted beams of light. Why should there be no wavelength dependence? It's in retrospect not surprising. Why? Because what we do in this concept is we match 2 points. The molecule is a point, sort of, and the zero of the donut is a point. If you match 2 points, the wavelengths here or the size of the donut doesn't really matter. It could be larger, could be smaller. So this is why the diffraction doesn't play any role. And this leads to a concept in microscopy that works entirely with focused light, yet there is no wavelength dependence, which is really striking. Okay, now in reality, there's no such thing as a demon, but in reality, you can come up with something that comes close to it. And that is the following. Rather than having a demon here, we have a controller that measures the number of detections. Of course, there will be some cases where the zero does not coincide with the molecule, and there will be some fluorescence emission and detections. And then the controller acts on the beam deflector. And what the controller does, the software does, it tries to minimize the distance actually between the molecule and the donut zero. And the better that match is, the fewer photons you need, and the better the precision will be. And then, of course, you can trace the position of the molecule with very high precision, yet you need much fewer photons than you would need, say, in a normal localization modality. Now, in reality, of course, it is done in the following way. If the molecule is supposed to be somewhere in between the 2 dots, the purple dot and the orange dot, how do we know now where it is? It's very simple. We scan this donut across the molecule, and once a zero coincides in space with the molecule, the fluorescence here is 0, and this is where the position of the molecule must be located, where the 2 coincide in space. So scanning it, the donut over the molecule, just tells us where the molecule is. It's very simple. Now, in reality, you don't even need to do that, because it's perfectly sufficient to measure the fluorescence that is found when the donut is at the endpoints here and here. Why? Because this curve here is very well known. This is a parabola. So the 0 is in first approximation parabola. And if you have the measured points here and 0 and 1, you can easily calculate where xm is. So you can instantly jump from here to here and find out the position of the molecule. So within this quadratic approximation, it's sufficient to jump from one place to the other. Then you can easily calculate where xm is. So this is a simple equation. and then you have the position. And this equation is very, very useful because it tells you instantly there's no dependence on the wavelengths and there's no dependence on the molecular orientation. And the reason is we put actually the burden of requiring many photons to localize the molecule on the excitation beam. In the past, it was on the emission beam. Here it is now on the excitation beam. And the excitation beam is perfectly controlled in space because that's done by the beam deflector and the laser. And so that's the deep physics behind it. So you always need many photons to localize something or to get a coordinate. But now the emphasis is put on the pattern of light with which you illuminate rather than which you detect. Now, if you calculate the precision with which the molecule can be localized, you will find, and that's not surprising, that it scales inversely with the square root of the total number of detected photons. So the more photons you detect, the more precise you will get, but it scales only with the square root, as we've seen before. But now the new thing is, it also scales with the average distance between the molecule and the position where the donut is actually placed. And this is only a linear relationship, and this is good because it means that once we have roughly estimated where it is, we can bring the zero closer and closer and closer, and the precision will go linearly up with this distance L. And so we have a handle on getting the precision up just by bringing the zero closer, as it is done in this thought experiment that I've shown you with the demon. Okay, so this is really important because, as a matter of fact, if we do it iteratively, the precision scales exponentially. So we can crank up the precision exponentially with the average distance, whereas here, of course, in the normal localization scales with the square root, which is, of course, very bad. So bringing the zero closer to the molecule really gets up the position. Of course, in 2 dimensions, you would not have 2 points, you would have 3 points, or 4 for that matter, it's even better. Without boring you with the details, of course, the precision still scales with L, and this is shown in here. So once you know roughly where it is, you bring the zero on average closer to the molecule, and the precision goes up. As a rule of thumb, this method of localizing molecules needs 100 times fewer photons in practice as compared to a standard localization modality, which is used throughout the world in thousands of labs. So I'm arguing they do it the wrong way when it comes to finding out the position of the molecule. Okay, so how does it translate in high resolution? It's very simple. Now, remember that these molecules that are arranged like this in a normal palm storm, which was given a share of the Nobel Prize, say 8 years back, couldn't discern the molecules. But now this method, MINFLUX, because of its high localization precision, because fewer photons are enough to get the high precision, you can separate them very, very clearly, as you've seen in the measurement. 6 nanometers apart can be clearly solved, not in palm storm, but in MINFLUX. So in other words, although we use just focus visible light regular lenses, provided that we separate by on-off, of course, that's clear, we can reach the maximum optical resolution of fluorophores. And as I indicated already, without wavelength dependence. The only wavelength dependence comes from the fact that, okay, we need to excite a certain molecule, and a certain molecule needs a certain excitation wavelength. Say some molecules need green light, some need yellow light, but the actual wavelengths really doesn't really matter because that's overcome. Now, can you take large fields of views? Of course, because the one I've shown you were just molecules at small distances. Yes, you just scan, for example, this donut over a field of view, and then you get pictures with a high spatial resolution, and of course with a high localization precision. So here it's below 1 nanometer. The median is 0.9. And if you look at it, so these are so-called nuclear pore complexes, similar to the structure I've shown on the you've seen on the Nobel poster, and here the resolution is much better. It's better by a factor of 10, and these little patches can be associated actually with individual molecules. Now, if we compare it with STED microscopy, which was developed, say, a decade back or more than a decade back, it's still worse by a factor of 10, and the standard resolution is worse by a factor of 100. So you have a factor of 10 here, another factor of 10 here. So now the resolution is better by a factor of 100 rather than just by a factor of 10. And the molecule scale has been reached. Now, not only can this method be used for imaging, it can also be used for tracking molecules, as I indicated already. And in order to demonstrate this, I have decided that we work on the tracking of a certain protein that is well studied, and one of them is kinesin. But before showing you this kinesin, I'm just indicating to you how this tracking works. So again, if a molecule moves like that on trajectory, we just quickly measure the positions around it and find out where the molecule is. And in this way, you can quickly track the position of molecule, and you can do that 50 to 100 times faster than before, than with a camera. Why? Because you need 50 to 100 times fewer photons, and then you don't have to wait for so long. And now I'm showing you this kinesin movement. Now, some of you may know that kinesin is a motor protein that walks on microtubules, and it carries cargo with it and neurotransmitters and so on. And when it walks, it makes steps of 8 nanometers. It is a hand-over-hand procession on microtubules. As a matter of fact, our precision is so good, that not only we could measure these steps, so this is just a measurement of the position here of this fluorescent molecule on the stalk of this kinesin, but we could also measure substeps, because we have a precision of below 1 nanometer attained within 5 milliseconds. In the past, because they required 100 times more photons, they needed 300 milliseconds to get the same precision. So we are faster. Then we can measure substeps, and the mechanistic details. And without boring you with the details of kinesin, I'm just indicating that we can measure much smaller steps because we can look with a higher temporal resolution into the details of the movement. And not only that, we can also use it to find out how this say heads, that's what they call, of kinesin just move. And this can be done, for example, by labeling the head here at the end. Then you watch how this fluorophore changes its position in space, and then you label it here and watch again how this fluorophore changes its position in space. These are the data. And so if we do that and measure the tracks, you find out mechanistic details that couldn't be seen before, and we could see that the steps have bias to the right and so on, and we found out about the details. I'm not going to speak about that. It's published, actually will come out very visibly soon. I would like to come back to STED microscopy, which kind of opened the field. Now, in STED microscopy, what you have is an excitation beam. You have a beam with this donut shape, which now turns molecules off, and then here, this is the remaining region in which the molecules are still allowed to emit. Now, this method is now being used in many labs throughout the world. It's very convenient, produces pictures, but as I said, only pictures that have a spatial resolution between 20 and 40 nanometers. So it's roughly a factor of 10 beyond the diffraction barrier. But of course, we have the ambition of getting better and better. And one way of doing it is to turn molecules on individually, as we've seen before, but now use this, say, coordinate targeted of STED in order to get a higher, say, precision information. And this can be done by making this donut, so to speak, circle around the molecule such that the zero coincides with the molecule in space. And then again, you have this phenomenon of injecting a coordinate and localizing it with a donut, making it very precise. And again, without going into the details too much, we have managed to locate molecules down with subnanometer precision. So 0.5 nanometers, 5 angstrom, and with 10,000 photons, we get down to 2 angstrom. So this is 10 times below the actual size of the fluorophore. So it's really crazy at room temperature. Some people did that before with low temperature, which has a lot of problems and vibrations, and not practical, really, especially not for biology, to see real movements, of course, because everything is frozen. We can see that at room temperature. And so molecules that are just 5 nanometer apart with this method can easily be discerned, as you can see here. So again, keep in mind, this is 150 times below the wavelength that is used. And if you put the size of the fluorophores in relation, like 4 nanometers, the size, 2 nanometers, the diameter of the fluorophore, they're just 4 nanometers apart, yet they can be discerned. So it really shows that we're really down with the resolution at the molecular scale. And these are so-called MINSTED pictures again of the nuclear pores. They all look different. If you average, say, 81 of them, say, in space, then you get a sort of average image of something, and this nicely fits actually with what you get from cryo-EM. But cryo-EM, by definition, gives only averaged pictures because it's taken out of many electron density scattering pictures. Here, of course, you still get the individual, say, situation of individual fluorophores. So to sum up, since my time is up, the physics part of fluorescence microscopy resolution is solved in my view. So the essence is that you separate them by preparing them in 2 different states for the measurement, for the time point of measurement, time point of detection. That has been the missing piece that kept fluorescence microscopy diffraction limited throughout the century. But this essence of discerning it by playing on and off with them, that actually broke the diffraction barrier. And then the maximum resolution has also been solved by doing it in such a way that the position of the molecule is found out not by looking at a pattern of light that is produced by the molecule and the fluorescence of the molecule, but using a pattern of light that is again produced by the laser, as it is done in STED microscopy, and matching that pattern with the position of the molecule. So this is arguably, in my view, the best way of doing it. And these 2 principles will be very difficult to overcome because they are really powerful and fundamental. And not surprisingly, they were the first actually to lead to a spatial resolution that is at the end of the day, as I'm showing here in this red sentence, no longer dependent on the wavelengths. And this is mind-boggling. I'm saying that. You have now in fluorescence microscopy, far field focused light fluorescence microscopy, a resolution that doesn't depend on the wavelengths anymore. The limits that are now set are set by the chemistry of labeling, fluorophore size, and this type of thing. And biologists now have to worry about this, and chemists have to worry about this, but the physics is sorted out. Applications are many: molecular maps, protein dynamics, drug discovery, you name it. And with that, I'm coming to my acknowledgement slide, showing the people who have really done the say practical work and experimental work in the lab. And we have a lot of fun developing this. And with that, I'm thanking you for listening so patiently. Thank you.
Thank you, Prof Hell. We now invite Prof Liu to moderate the Q&A.
Good morning, Professor Stefan Hell, and good afternoon, ladies and gentlemen. So next time when you walk into a laboratory, right, you can ask a good question, right? Are you using a microscope or are you using a nanoscope? Because now with Professor Stefan Hell's work, right, the resolution of the so-called microscope goes from 1 micrometer to almost 1 nanometer. That's a remarkable work and a wonderful talk. So now is the Q&A session. So the first question is Lily, please. Yeah.
Hello, thank you, Professor Stefan. I'm Isha from Cambridge doing computational biology. I used some deep learning methods to do like confocal imaging analysis. So I'm curious, like, could you please give us some comments on using machine learning methods on your molecular fluorescent like imaging analysis, like 2D or 3D segmentation, cell tracking, or cell-to-cell false inference?
Yes, it's a very good point that you're raising. It's very clear that the methods that I've developed here and discussed here are purely physics-based, if you will. And of course, there's a huge potential in taking advantage of the methods that were developed in data sciences, including say artificial intelligence and on all these interesting, say, approaches that are coming up right now. Of course, there's a lot of potential in interpreting the data, segmenting data, as you mentioned, in a much more clever way as it is done, as it has been done so far. And the combination of applying, say, new computational algorithms, whatever that is, artificial intelligence, and so on, both for evaluating the actual measurements, so evaluating the photon traces and evaluating the biological outcome, will be definitely a very, very interesting topic for the coming years. And these methods now that are being applied to structure biology and any other fields, of course, will be applied also to fluorescence microscopy to great effect, I'm sure.
Thank you.
Okay, we also, okay, this gentleman, please.
Thank you, Professor, for this wonderful talk. So my name is Neelkant. I am from India working in Hong Kong. So as you showed that the precision of this microscopy is scales as 1 by square root n. So however, like by using quantum effects like quantum imaging, the scaling can be 1 by n. So I wanted to know what is the current experimental progress in quantum imaging for microscopy and what are the main challenges to be overcome in this field?
Yeah, so to be very clear, so in the past, yeah, the scaling was 1 over square root of n. Here, in the methods I've shown, it's not 1 over square root of n. Yeah, it is only if you stay with it. Actually, it's exponential. So the thing is that if you bring the zero closer to the molecule, then it goes exponentially with the number of photons. And this is why this is, as I said, very hard to beat. If you take advantage of quantum, say, non-classical light and all this type of stuff, you may get 1 over n, but it will never be the exponential. This is why I personally believe that that the methods that I've shown here, because it has this exponential increase of the precision, yeah, with the number of photons, it's still superior to any of these so arguably fashionable quantum imaging modalities.
Thank you.
Okay, Professor Stefan Hell, we also have many online participants and they raise many interesting questions. So let me just flash one question to you. What do you think the next step is? Will it be possible for someday achieve a laser or light focus of 1 nanometer or even smaller than that?
Yeah, well, that'll be hard to do, of course, for obvious reasons. I mean, it's Heisenberg's uncertainty principle that has to be applied to photons. So I discovered that this of course is the wrong way of thinking about the resolution. To try to focus the light down to 1 nanometer. That's why I gave it up. I said that there's no point. Of course, people have tried that. Actually, they tried to squeeze the light down to tiny holes, so-called near-field optics, and this has been actually Eric Betzig's first approach. And I realized that this is the wrong way. This is completely the wrong way, because the light doesn't want to go through tiny holes, because the light wants to be diffracted. And so so let it diffracted, let it be diffracted, and then use different ways of separating molecules, not just through the focusing of light. Use and do not separate by photons, separate by states. Yeah, and so that was actually the major, say, lucky moment of my life when I realized, oh, I can break the diffraction barrier just by making the molecules different for a brief period of time. For the time of point of detection, it's different from the rest, namely by having them in different states. Then you don't have to worry about the focusing. Yeah, and this is actually the key, and I think this is very hard to beat. So doing it by trying to get a focusing more sharply in the wide field, in the most focus light, that'll be hard. I don't know how that will be done. So one should never say never, because you never know what's coming up, and physics may bear some, or may have some surprises in store. I don't know, but but I don't see how that is done. I don't see that because so Heisenberg's principle needs to be applied to photons in that case, and I've not seen a violation of that, a serious one at least.
Seems that's a very difficult task. Okay, the next
Yeah.
question is also on the technical side, and it asks, the donut-shaped beam would need to have a dark center, which should be very small, small enough to allow precise localization. How do you actually achieve that?
Yeah, the donut center is actually literally a point because it's statistically defined by the photons that are surrounding the donut. I mean, the donut is of course a pattern, yeah, but the point where there is no photon showing up is of course very confined. So the 0 point, of course, is if you will, like a singularity. It's extremely well defined, and the more photons you use, of course, for making that donut beam, the better defined in practice will be that point in the center of the donut. And so the good thing is that there is zillions of photons coming from the laser. There's no problem actually. There's no problem actually in defining that 0 point. So that can be defined to angstrom precision, and that's why it's not a big deal. So that's a strength of the method is that the burden of requiring many photons to define a coordinate is actually placed from the fluorescence emission, from the fluorescence photons, yeah, that are always limited and prone to stop, put on the laser, which of course is very reliable and produces zillions of photons in no time. And that's why it's so difficult to define a coordinate with laser light rather than with light that is produced by a fluorescent molecule, which is of course constantly going on and off and reaching and the rest. And that's the fundamental insight why we get this very, very high precision, because it's done with laser beam rather than with fluorescent beam produced by a molecule.
Okay, thank you, Prof. So we have the last on-set question. Please, this gentleman.
Yes, hello, Professor Hell. Thank you for your presentation. So I'm also working with fluorescence microscopy, so I've been following your work for a while already. And I'm wondering, so now that you, let's say, brought the resolution down to the molecular scale and the physics is kind of solved, what are you up to for the next 10 years? I mean, where do you want to go? Is it larger samples, multicolors? Yeah.
Yeah, it's a good question, actually. The answer I gave implicitly, I would say, in the talk, it's the dynamics. This is, you've seen that I spoke about Kinesin or so, and why? Because this is the only method that I know of. I really mean it. The only method that I know of that can give, that can measure the dynamics or the movements of molecules, biomolecules, at room temperature with nanometer precision in the millisecond domain. And this may even go up because the measurements I've shown are just first steps in the field. But this is the way to go when you want to see movements, for example, in cells of proteins, the conformational changes of proteins in cells under physiological conditions. And in my view, this field is likely to turn out to be as important, if not more important, than plain super resolution fluorescence imaging per se. And this is, in my view, a completely new field. People have not fully appreciated that and realized that, because it always takes some time to realize it. But if I'm thinking here, sitting here at my desk and trying to think, envision the future, so to speak, of the field, in my view, this is going to be a game changer, because there's no other method which allows you to really see how something moves on the nanometer scale, say at the scale of the molecules themselves, the scale of the proteins themselves. With imaging, you can always argue, well, there is EM and cryo-EM, and there is this, and there's atomic force, and so on. But dynamics on that scale, no other method can do that. There's only MINFLUX and MINSTED that could do that right now. And I don't see, because the concept is so strong, I don't see serious competition.
Okay, super. Looking forward. Thank you.
Okay, due to the time constraint, we'll have to stop here. So finally, let's thank Professor Stefan Hell again for the wonderful presentation.
Thank you.